In the current unit that we are studying, which is Unit 1, electricity, quantum phenomena and particle physics, we've just recently covered the current voltage characteristics of resistor, filament bulb and a semiconducting diode. If we first look at the resistor, the current voltage graph for a resistor is as follows. Now generally we've been plotting the current on the y-axis and the voltage on the x-axis. You could do it the other way around, but generally in the AQA exam this is how the graphs will be represented. What we found was the graph was shaped like this. So it was a straight line graph, and what we can normally do from a graph is measure the gradient. So if we look at the gradient, we've got the change in current here, we've got the change in voltage here. Gradient is change in current divided by the change in voltage. And what we do know is that the gradient of a current voltage graph for a resistor is the conductance. Now if we want to get the resistance, we need to take the reciprocal of this. So 1 over the gradient, or 1 divided by conductance, is the resistance. Probably need the resistance more often at present than we are going to need the conductance. So this is what we need to know about a current voltage graph for a resistor. Excuse me. The final thing is that it is an ohmic resistor because it follows Ohm's law. So that means as the voltage increases, the current also increases. If you say double the voltage, then the current will also double. So it's a linear relationship. The second component we have looked at is a filament bulb, and this gave us a slightly different relationship. So for the current voltage graph of a filament bulb, we got a curve-shaped graph. This told us that the filament bulb, the resistance changes. So as you can see, the line is curved, the gradient is changing, the resistance is changing. Now, if we picked, say, 2 points, on this graph and used Ohm's law, which is R equals V divided by I, so if we took this point here and say this point here, what we would find is that the resistance here, when the voltage is higher, is greater than the resistance down here when the voltage is lower. This is to do with the voltage giving the atoms in the lattice energy, and this makes the atoms in the metal lattice vibrate more. Therefore, the electrons collide with these atoms that are vibrating even more often. So there's more collisions between electrons and the metal ions or stroke atoms that are vibrating. The final component we looked at was a semiconducting diode, and the diode graph was very different to the previous two. It looked as follows.
It's a long story.
So what this was showing was that for small voltages, so around here, that not very much current was flowing in through the diode. As we then had little increases in voltage, that had a big increase in current. So here we are talking about probably 2 volts, obviously depending on the diode or the rectifier in its actual the input that it can handle, and this was called forward bias. So this meant that basically the current could flow easier through this direction in the diode. Now generally from GCSE what you've been told is that a diode only lets current flow one way. That's true to a certain extent, but you can increase the voltage as to overcome this effect. So if we switch the diode in our circuit around and increase the voltage much more in the opposite direction, then you can force the current to flow through the diode. I'm just making up numbers here, but we're probably talking about something like 15 to 20 volts maybe for the current to flow the other way. Now the ones we've got in school would burn out at this point, and you'd basically get no results. So we only ended up with this half of the graph. Everybody in the class got that, which was excellent. It's just being able to explain what's going on inside the semiconducting diode that is a slightly more difficult part. That's coming on the next slide. So when we're talking about current flowing in this direction here, we're needing really large voltages. What we call this is reverse bias. So that means current's flowing in the opposite way, the way that it's not doesn't find it as easy to flow in.